let us try to see in this one different types of modules that are used in a membrane separation system. So first of all, we need to think about what are the flow patterns that are there in a membrane module. So for example, in the first case, in this case, A case, you can have both sides, the feed side as well as the permeate side, well mixed. So again, well mixed means the concentration anywhere in the system is equal to the outlet concentration. Or you could have a counter current flow of the feed and the permeate across the different modules, across the membrane that is being used for separation. Or you could have a co-current flow between the feed and the permeate, or you could have a feed going in a plug flow and the permeate coming out could be combined and then going out as a permeate stream. So permeate concentration, permeate stream would be different at different locations, but when it comes out, it is a combined stream. So you can have different flow patterns. So what we have seen so far is how flux is related to pressure difference and the concentration polarization, or if it's a batch process, how the flux is dependent on degree of fouling. So we may need to integrate this across. If it's a continuous process, we would need to integrate the flux and the driving force, get an expression for flux versus driving force, and integrate that over the length, so as to be able to calculate the area of the membrane required. Just like we calculate for a given conversion how much reactor volume would be required if it's a CSTR kind of operation, or if it's a plug flow kind of operation. In this particular case, we would be trying to write the flux, and therefore we would be able to calculate the membrane area required in a well mixed manner, in a well mixed operation, or in a plug flow operation, or in a counter current operation. So driving forces are going to change when we are looking at the concentration recovery in a counter current manner versus co-current manner. And we can right now we will not go into those many details, we will not calculate actually, but you can appreciate how the concentration differences will change, how the fluxes will change, and how in turn it will affect the area required for membrane in all these four cases. Even if the end points, the feed and the permeate and the retentate, even if the end conditions are the same, the area required would be different, just as we had seen in CRE when the reactor was well mixed or reactor was plug flow, we get a totally different value of the reactor volume. In terms of the very basic shapes that are there, this is what we had seen very early. We had like a thin film composite membrane. We had a thin active layer, and that was resting on a support. Now, from this basic shape, you can go to various options, various membrane devices. Imagine, for example, you take this basic shape and you rotate this, or you transform this into a tubular shape. So this would become a tubular membrane where feed would go in one side, there would be an active layer. So let's say this is a cross section of the tube you are seeing. You are essentially seeing this as a support. There is an active layer in the just inside this, and feed will go in the inside and permeate would come out. Or we could have feed going outside and no. So in this case, the thin layer is inside, so feed would be inside and permeate would be outside. If the thin layer is outside, then we would have feed in outside the tube and permeate coming inside the tube. You can of course integrate this in a multi-tubular channel. So you could have each tube inside a porous support, and then when feed is going through, permeate will go through this porous support, and combined permeate will come out, just like we had seen here. You can also think about this basic shape trying to put into a plate and frame kind of module. So imagine your plate and frame filter that you studied in your undergraduate course. It is very much similar to that. Or a plate heat exchanger that you had seen in heat transfer. It is very similar to that. So there is a permeable membrane, there is a support, and then feed would go on either side, and the permeate would come in and then go out through one of these tubes. Or the basic shape of a thin membrane, we can roll it in the form of a spiral wound module. So this is how a spiral wound module would look like. So if you imagine that this is the central tube over which this membrane is wound, the flat sheet is wound, So you can see that the flat sheet forms a sort of a spiral around, and there are feed spacers. So just to promote the turbulence, we had seen when we had talked about membrane fouling that the turbulence promoters will increase the mass transfer coefficient and reduce the concentration polarization. So the feed spacers, so imagine that the feed is going across this module. You might have also seen in a spiral heat exchanger how the flow patterns are. This is very similar to that. So feed is as if going into the plane of this screen. It is permeating into the permeate side, and then there could be a permeate spacer to increase the turbulence there, and then this permeate would spiral inside into the central tube, and it will come out from one end of the central tube. So this is called as a spiral module. So the spiral modules are designated based on their diameter and based on their length. There is a universal nomenclature which we do for designating the spiral modules, and I would like you to do homework and find out about how the spiral modules are given name or a given number, say 80-20 module or 80-40 module or a 40-80 module, depending on the diameter and depending on the length of the module. So that decides the area of the module. Or you could have the tubes into a multi-tubular, like a shell and tube exchanger format. So you would have tubes which are membrane, which have the membrane, and then you would have the flow of the feed and the permeate and the retentate on either sides of the tube. Or you could make these tubes very, very small. So they are called as fibers. So imagine this is a cross section of a fiber. So this is a SEM image, a very much enlarged image of a fiber. You can see the porous nature of the fiber, and the thin layer is on the inside of the fiber. So imagine that several such fibers are used. You can see that how thin each fiber is, and a bunch of these fibers can be put into a module, and then this would give very large surface area per unit space of the module. So these are very common in various biomedical applications like dialysis, for example. Okay, just to compare different modules, so plate and frame in terms of various parameters, plate and frame, spiral, tubular, hollow fiber, we are comparing in terms of how much area they offer for filtration per unit volume of the module, how much resistant they are to fouling, what is the ease of cleaning, and what is the cost. So for example, plate and frame, you will not have very high surface area per unit volume like a plate heat exchanger, but because the spacers, you would have a good resistance to fouling. You can of course dismantle and clean the operation, but the cost would be high. Whereas spiral, you will get a very large packing density in terms of meter square per meter cube. Resistance to fouling would be high because of the spacer modules that are used. Cleaning would be not so easy, but you could always have some chemical cleaning being done. And you can, of course, the cost would be very low because it's essentially a flat sheet which you're just winding around. Tubular, where you will have multiple tubular in one unit, so again area would be less, but you would have a good resistance to fouling, good cleaning, cost would be high. Hollow fiber, the fibers are so small that you can get a very large surface area in terms of a unit volume. That's why it is very popular in medical applications. But of course, the resistance to fouling is poor because we don't have any turbulence inside. There are no turbulence promoters, and therefore the fouling tendency would be large. Cleaning also would be difficult because I can't remove individual fiber and clean. We would be only able to clean in terms of by chemical cleaning. But of course, the fibers can be made by spinning, and you can make a very large length of the fibers, and you can have a very low cost of a module. That's why it is so popular for dialysis applications for kidney patients. Just to look at different applications, different processes, let's imagine a batch process. So here is where we will feed our solution to be concentrated. Let's say we will pump it through a module. Now each of these modules could be a plate and frame module or a spiral module or a hollow fiber module. We will get permeate from one side, so it is only a schematic representation, and the retentate could be recycled back into the feed tank, or to maintain enough cross flow velocities, we could recycle the retentate back to the feed by means of a booster pump. So this inner loop may or may not be there. So essentially the feed is being circulated through the membrane back into the same batch tank or feed tank, if you would like to call that. Just some nomenclature. So imagine that in the feed tank, the volume is V at any instant of time. Of course, as more and more permeate is collected, this V will reduce. Concentration in the feed will increase if you are trying to remove the solvent. It goes through the membrane module. Cp is the permeate concentration, Cr is the retentate concentration. Let's say Vi is the initial volume, Ci is the initial concentration. In the membrane batch tank, V is the volume at any point of time, C is the concentration at any point of time. The final volume is Vf, the final concentration is Cf, retentate concentration is Cr, permeate concentration is Cp, solute rejection is R. Now, as this volume goes down in this feed tank because some permeate is removed, the initial volume and the final volume, the ratio is called as volume concentration factor. Just a small correction. Let me just do that here. This is Vi by Vf. So volume initially is large, volume finally is small. So this is Vi by Vf. So volume concentration factor is more than 1. So volume concentration is, let's say 5, then initial volume, let's say, is 1000, the final volume would be 200. That's why this volume concentration factor is more than 1. I would like you to plot qualitatively the variation of following parameters with respect to time. I would like you to plot qualitatively how the volume in the batch tank, the feed tank, changes with respect to time, how the concentration in batch tank changes with respect to time, how the permeate concentration and flux would change with respect to time. So do this exercise before going forward in the video, right? Then only continue with the video. So if we try to write a material balance for change in the solute concentration in the feed tank, okay, we want to write a balance for the solute in the feed tank. Okay, so write the equation, then only go forward. Don't do this exercise for yourself. So if we write an expression d of Vc, that's the change in solute concentration, V multiplied by C is the solute concentration at any point of time. So derivative of that is how the solute concentration will change with respect to time, and this is equal to whatever is going out. So if you take this whole thing as a control volume, whatever is the change in the batch tank, that has gone out in the permeate. So this must be equal to the permeate concentration multiplied by how much volume has gone in the permeate. So if we simplify this, we will get dV by V is equal to dC by Cp minus C. Now I would like you to integrate this from initial time t equal to 0 to the final time t equal to end. Again, integrate this for yourself and then only go forward. So just to help you do this, if the change in solute concentration across the module is small, so that means the change in concentration across the module is small, right? Which means this change takes very long time as compared to the residence time in the module. If this change in concentration in this across the module is small, then the rejection we can say is 1 minus Cp divided by C. Now we can integrate from initial to final conditions. I would like you to integrate and relate the initial and final concentrations and volumes. So do that, pause the video, do this integration and then only go forward. So here is what you will get. So dV by V integrated from initial to final, Cp minus C integrated with respect to dC from the initial concentration in the batch tank Ci to the final concentration in the tank. So if you write this properly, integrate this properly, you will get Cf by Ci would be Vi by Vf raised to R, and Vi by Vf is nothing but our volume concentration factor. I would like you to write an expression for quantity of solute that remains in the batch tank at the end in terms of the initial amount. So we call this as the yield of the solute in the batch process. So this is our expression for the change in concentration. If I write yield, it will be how much solute is remaining at the end divided by how much solute is there initially. So if you substitute this expression, you will get volume concentration factor raised to R minus 1. What I would like you to think about is how the flux will vary with volume concentration factor, and then how we would relate the average flux to the initial and final flux. So do this. We are not going to do this uh, in, uh, in the course. So let's take a small problem. Imagine that there is a 1000 liter fluid solution with an initial protein concentration of 10 grams per liter. Membrane shows a rejection coefficient of 0.7. If it is required to concentrate the feed in 4 hours to a volume concentration factor of 5, find the yield. Also, if the average flux is 20 liter per meter square hour, find the area. Okay, so do this problem yourself, and then you will see, and then you can go ahead and see the solution. Okay, the problem is very straightforward. So initial volume is just the definition of volume concentration factor. Initial volume is 1000 liter, final volume is, volume concentration factor is 5, so final volume is 5 divided by 1000 divided by 5, that's 200 liters. Permeate is 800 liters, right? So if permeate is 800 liters, that is 1000 minus 200, that's 800. So area would be total permeate divided by the average flux. So 200 divided by 20 liter per meter square hour, and we would like to do this in 4 hours. That means the area should be 10 meters square. Now the final concentration, if we write in the membrane, so in the batch tank, CF by CI would be VCF raised to R. So VCF, that is 5 raised to 0.7, which means 3.08. So final concentration would be 3.08 times the initial concentration. Final concentration would be 30.8 grams per liter. Yield is how much has remained at the end, 200 into 30.8, 200 into 30.8 divided by what was there initially, 1000 multiplied by 10, that's 0.616. So 61% is how much the solute is retained inside the batch tank. 39% has gone out to the permeate. Okay, so if we there is another paper by these authors in 2002 that presented a simpler model for the flux decline. What this model does, this was their geometry. What this model says is that dJ by dt, the change in flux in the membrane, is related to two things. One is how much concentration is brought to the membrane surface. That's going to be dependent on the flux itself. So more the flux, more the blocking or more the fouling. At the same time, if I have the cross flow of the feed, that cross flow is going to clean the membrane by way of turbulence around the membrane. So it depends on the Reynolds number. So the mechanism of flux decline is how much fouling is proportional to how much fouling happens because of the flux, and how much cleaning happens because of the turbulence that's related to the Reynolds number. So if you take a particular geometry, particular flow rate, Reynolds number is just a constant, and these are also constant depending on the operation. So minus dj by dt is a j minus b. So if we integrate this at time t equal to 0, let's say flux is j0, and then we can now integrate this as j equal to j0 e raised to minus a2 plus b by a into 1 minus e raised to minus a by t. So if you put time t tending to infinity in this particular case, you will see that the flux is limited to a value b by a, and b and a are just the constants for a particular operation, for a particular module, for a particular concentration, for a particular flow rate or velocity across this membrane cartridge. This is a very simple model. You can see this paper, they have given some data and applied this to their own data. What we would like to do is really how to relate the J to change in volume in the batch tank, and then you can simplify this further with respect to J as minus 1 by a dV by dt, and relate the how volume in the batch tank here changes with respect to time. So again, this is the exercise left to you. You can do this yourself. Just the maths will be a little bit more complicated, but you can do this later. Another problem that happens in a batch filtration is that as the volume concentration factor increases, the flux declines because the increase in feed concentration. Also, if the increase in feed concentration But if the feed concentration increases, the permeate concentration also starts increasing because of the solute going into the permeate side. So, in addition, because of the increase in concentration, the concentration polarization, the reverse osmosis gradient, osmotic pressure gradient increases. We have seen that in the last session when in the problem, when the initial and the final flux was final effective driving force by changing by factor of 3. Recall this problem. Recall this problem. Right? So now that's a problem in a batch process, right? So that's a problem in batch process. So the way we could overcome that is if we keep the concentration under our own control. So for that, what we do is we do periodic addition of the solvent so that the solute gets diluted here and the flux can be maintained. So this is a good option if we want to recover, let's say, solvent as a permeate, but it's not a good option if we are trying to recover the solute as a concentrated mass, because then we are diluting all the time. So this is called as a diafiltration. So it helps in removing the permeating solute completely from this permeate. Okay, let's just take a small problem. So let's just say we have a 10 meter cube of an aqueous solution containing solute at an initial concentration of 0.02 molar. It is to be concentrated to 2 meter cube. So 10 meter cube is to be concentrated to 2 meter cube at a transmembrane pressure of 3 bar, 30 degrees centigrade in 3 hours. Let us assume that the polarization modulus is 1, rejection is 1, just to make our life simple. At 3 bar, membrane gives a pure water flux of 100 lmh. I would like you to calculate the membrane area required. So remember, polarization modulus is 1. That means the concentration near the membrane surface and the bulk is the same. This is just to make your life simple. But the permeate concentration is 0. Therefore, there will be a substantial osmotic pressure gradient which is opposing the applied transmembrane pressure. So take that into account and then go forward. So I would like you to calculate the membrane area required. So do this problem on your own. Try that. Then only look at the solution. Okay, so again, polarization modulus is 1, so that means Cm is equal to Cv. R is 1, so delta P is nothing but the bulk concentration, or C in general, RT. So pure water flux is, remember, for pure water flux there is no osmotic pressure opposing the applied pressure gradient. So the flux would just be delta P by Rm. Most importantly, take care of units while calculating. So now you can solve the problem before you go to the next slide. Okay, so here is the solution. First, let's find the membrane resistance. Membrane resistance is nothing but delta P divided by JW. So there is 3 bar divided by 100 lmh. So it is 0.03 bar per lmh. Now, if we write the definition of flux, J would be minus 1 by A dV by dt. So I can rearrange this. dV by dt would be A. J now would be delta P minus delta pi divided by Rm. Delta pi is because there is no permeate flux, there is no permeate concentration. The feed concentration is changing. So this delta pi we can write in terms of CRT. So now imagine that this C is changing with respect to this T. So in this dV by dt, A is what we need to find out. Rm is constant, delta P is constant, RT are constant. R is not this rejection, R is universal gas constant in Van 't Hoff equation. So this C is changing with respect to time. So I have to relate either C to volume, or I can relate this volume to C. Easy way to do it is this C, if I write in terms of VI CI divided by V, or we could have written this from our BCF relationship earlier that we had derived. So if you substitute this now, everything on one side dV and dt on the other side. So integrate this from initial volume to final volume, 0 to t, right? So substitute, integrate for yourself. You might like to use the calculator, but take care of units. This volume is given in liters. Rm is given in terms of lmh per bar per lmh. Delta P is given in terms of bar. CI is given in terms of gram mole per liter or molar. R you have to take care so that you will get units of pressure correctly. Or if you are using R in SI units, divide by the conversion factor 1 into 10 raised to 5. So substitute and you will find that area required is about 45 meters square. Okay, in a continuous tangential flow filtration, you have a feed coming in all the time. There's a membrane module, permeate comes out, reject comes out, and just to maintain high velocities in the membrane module, just to take care of the turbulence and to take care of the concentration polarization, we recycle lot of the retinted back into the feed side. Okay. So now volume concentration factor would be QF divided by QR. If recycle ratio is large, then we can write R as 1 minus the concentration here divided 1 minus the permeate concentration divided by the concentration in the membrane module. And because recycle is large, the concentration in the membrane module would just be the same as the reject concentration or the retentate concentration. So using these, I would like you to derive an expression for CR by CF, and yield in terms of the volume concentration factor and R, just like the same way we had done for the batch process. Again, do for yourself, then only go forward. Pause the video. Okay, so here is an answer. We would like to write material balance first. So QF would be QR plus QP. If I write in terms of the solute mass balance, QFCF would be the solute coming in to the membrane module. QRCR is what is rejected. QPCP is what is permeated. Substitute for QP in this second expression from the first equation and simplify. You will get this expression. Now this ratio QF by QR we can write in terms of the volume concentration factor divided by CF as well. So we'll get CR by CF. You will get CP by CF here. CP by CF you can write in terms of CR and CF if you use the rejection coefficient definition properly. So you will get CR by CF is nothing but VCF divided by rejection of the membrane plus VCF into R minus 1, or yield if you want, it will be QRCR divided by QFCF, it will be 1 divided by R plus VCF into 1 minus R. So you stop here this lecture here. What remains to be seen is now some more applications such as reverse osmosis and pervaporation and then gas separation.